Okay, so we are finally ready to look at Shor's algorithm. This is perhaps the most famous quantum algorithm in the quantum computing literature. At the very core of the algorithm, there is this clever use of the quantum Fourier transform on periodic superpositions and transforming these superposition states to a more suitable form so as to help us fetch the period of the given function. So the algorithm uses two registers. Okay, suppose that n is the integer that we want to factorize. Let me actually draw the circuit diagram as we go. So we have two registers. First register holds, it stores the binary representation of the integer, of the square of the integer that we want to factorize. Okay, so the first register will store the binary representation of the square of the number that we want to factorize. So if n is the number that we want to factorize, then the first register of the algorithm stores the binary representation of m, where m is at least as large as n squared. So it stores an m qubit, it's an n qubit register, m qubit register, where m is equal to log m, right? And the reason that m should be at least as large as n squared is the following. So we compute at least n squared different values of the modular exponentiation function all in parallel. Since r is less than n, there can be only r many different function outputs. So the period, the period must manifest itself in the resulting sequence of n square function values. So this is stored in the second register. So then the second register will store a number mod n. So this is an n qubit register. Okay, where n is equal to log n. Okay, so this is a register which can store a number mod n. Okay, let's write these down. First register stores a number as large as n squared, that is m, and the second register stores a number modulo n. Right. So, okay, so Shor's algorithm begins by initializing both registers to all zeros. Okay, so this is all zeros. Both registers are initialized to all zeros. And what we do first is that we apply the quantum Fourier transform on the first register. Quantum Fourier transform. Actually, in some books in literature, this is replaced by the Hadamard transform of an m-dimensional Hadamard transform, but they practically do the same thing. So first we apply the quantum Fourier transform on the first register, and the outcome will be a general superposition state of all basis states with equal amplitudes. On all zeros. So remember, this is of length m. Okay. All right. Now, after applying the quantum Fourier transform on all zeros, what we get is the same effect that the Hadamard transform would do on all zeros. So we get a superposition, a general superposition state of all basis states with equal amplitudes. That is 1 over square root m. So we get 1 over square root m from x equals 0 to m minus 1. We have x, and then we have all zeros. Alright, so next we apply the quantum version of the modular exponentiation function. Okay. Let's call this step 1. Well, actually, step 1 is to initialize registers to all 0. And then the second step is to apply the quantum Fourier transform on the first register. Third step is to apply the quantum version of the modular exponentiation function. And let's call it u f a n x. Okay, so u f a n x is simply is equal to a to the power x mod n, but it's the quantum version, the reversible version of the modular arithmetic function, the modular exponentiation function. Here a is a randomly chosen integer such that a and n are relatively prime. Okay. A and n are relatively prime. So a is chosen randomly. So a and n being relatively prime means that is the GCD of a and n is equal to 1. Okay. And after applying the modular exponentiation function on the second register, what we get is 1 over square root m from x to m minus 1. In the first register we have the superposition state x, and then we have f of x. So we have x and the corresponding f of x. Okay, so we have the entire superposition. All right, so what we do next is then measure the second register. Let me complete the picture. So here we apply the modular exponentiation function u f. Okay, and this is equal to a to the x mod n. And then next what we do is that we measure the second register. We measure the second register. Let me erase this part. Okay, so we measure the second register, and then we obtain a random integer a to the x mod n. Okay, so we obtain f of x. But recall the partial measurement that we did a couple of weeks ago. What we're doing here is a partial measurement. Okay, we're not measuring all qubits, but we're measuring some of the qubits. We're measuring the second register. Now, as soon as we measure the second register, and so we perform a partial measurement, anything in the superposition in the first register which is inconsistent with our measurement outcome will disappear, right? So I think we gave this example earlier that if we have a four-dimensional quantum state, a two-qubit quantum state. So for instance, if we have something like 0, 0 plus 0, 1 plus 1, 0 plus 1, 1 state, and if we get to measure if we measure the second register as 0, okay, second qubit, if we measure the second qubit as 0, then the outcome state will be 0, 0 plus 1, 0, right? So these two states will be inconsistent with our measurements. So they will disappear instantly. And this is what happens when we measure the second register. What we are left here is the only states left in the superposition in the first register will be the integers x, whose a to the x mod n is same as the measured value. Okay. And moreover, the only non-zero basis states, by which I mean the basis states with non-zero amplitudes, will be those states which are multiples of r plus some offset t. Okay, so when we step 4, measure the second register. So this is a partial measurement, and the only states left in the superposition in the first register are those integers x, whose a to the x mod n, whose f of x is same as the measured value. And all the other states, all the amplitudes of the other states will be 0. So the only non-zero states, that is states with non-zero amplitudes, will be the multiples of r plus some offset t. Okay. Now, in the beginning, we said that we assume that R divides M. Okay, so for simplicity, we assume that R divides M, the period R divides the size of the input vector here. And this is for convenience and for simplicity, but I can assure that the general case as well works as well. That is, Shor's algorithm also solves the case that when R does not divide M. Okay, so assumption R divides M, but we should note that Shor's algorithm works as well when R does not divide M. And all the essential ingredients are still here. Okay, so we're not missing anything. Now the general picture will look as follows. So we have a superposition state, a periodic state, and the only non-zero states will be the multiples of R. So suppose that this is state 0. Here we have the basis state R. Here we have 2R, 3R, and so on. Okay, and suppose this is M over R minus 1 times R. Okay, we have some offset here as well. In the worst case, let's suppose that we have an offset t, and other non-zero states will be R plus t, 2R plus t, 3R plus t, and finally M over R minus 1 times R plus t. Okay, and all of these will have the amplitude. So since the dimension of the vector is M, and since the period is R, so we have 1 over square root of M over R. So this is square root of R over M. Okay, so each will have the amplitude square root of R over M. The amplitudes beta j, and these are the basis states j. So then the state of the first register after measuring the second register, let's rewrite this. It will be it will be 1 over square root of M over R, and that's simply equal to square root of R over M, summation j from 0 to M over R minus 1. So we have multiples of R plus some offset. Also note that the distance between the non-zero states gives us the period of the function. So this is exactly what we want, right? So distance between the non-zero states, this is R, right? The distance between the non-zero states. But how do we get that information? So we want to find r. This is the value that we are looking for. And we ask the following question. Well, can we find r by measuring the first register at this point? Well, that doesn't work because all we would get is a random point in that case. And can we do this over and over again to find an approximation to r at least? Well, there is no correlation across independent trials because this offset value t is a random value. So here's what we do next, and this step will be the critical step in Shor's algorithm, and it does the magic trick, okay? So we are in step 5. Step 5. Step 5 is that we apply the quantum Fourier transform again on the first register. So let me complete the diagram. So we apply the quantum Fourier transform on the first register. In some books you will notice that they replace this with the inverse of the quantum Fourier transform. Well, the result doesn't change, they're all the same. And then we measure it. So let's see what happens here. All right, so now before measuring the first register, before the quantum Fourier transform, the first register is in this state, right? This superposition state. Now, when we apply the quantum Fourier transform on this state, what we will get is 1 over square root m over r, j from 0, m over r minus 1, jr plus t. This state will be mapped to, after applying the quantum Fourier transform, it will look like something along the lines of summation j equals 0 up to n minus 1, some amplitude beta j. It will eliminate the offset and it will change the amplitudes. Alright, so we need to figure out what beta j looks like for each j. Particularly, let's examine when j is a multiple of m over r. Okay, so let's look at the states where j equals some multiple of m over r. We want to know what beta k times m over r is. That is let's look at beta k times m over r. Now on this amplitudes, it'll get contribution from every part of the input vector, the normalization factor of the quantum Fourier transform, and a phase value of the products of these two basis states, the basis state jr and km over r. normalization factor of the quantum Fourier transform and phase of the products of JR and K M over R. So let's explicitly write beta K times M over R. So we have the coefficient comes from the input vector, right? So that's j from 0 to m over r minus 1, 1 over square root m over r. Then we have the normalization factor of the quantum Fourier transform, and that's 1 over square root m. And then we have the phase values, the product of the phase values of JR and Km over n, Km over r. So omega to the power JR times Km over r. So let's simplify this. This is summation j equals 0 to m over r minus 1. This is simply square root r over m times 1 over square root m times what we have left here is omega to the power j k m. So since any multiple of omega to the m is equal to 1, this simplifies to square root r over m times 1 over square root m. And we can simplify this to, so we have square root r over m times 1 over square root m. Well, we have m over r many of these, m over r times square root r over m times 1 over square root m. And here we have m over r times square root r over m, and this is equal to square root r over r. This is simply 1 over square root r. Now the rest of the amplitudes, when j is not equal to k times m over r, when j is not equal to k times m over r, beta j is equal to 0. So we have a constructive interference at the phase values beta j when j is equal to km over r, but we have a destructive interference at phase values beta j when j is not equal to k times m over r. Alright, so now that we have applied the quantum Fourier transform on the first register, and now we have a superposition state with period m over r with no offset, and the only basis states with non-zero amplitudes are those which are multiples of m over r. Okay, now the picture it looks very similar to the earlier one. So now we have r, 2r, 3r, okay, m over r minus 1r. All right. So this was the state before the quantum Fourier transform, and now we have another superposition with. Let me erase this. We have a similar superposition, except that the period is m over r this time, okay, and the offset is gone. So right now we measure the first register. And what we obtain is a random multiple of m over r. Okay, so step 6. Now we have a superposition state with period m over r with no offset, where the only basis states with non-zero amplitudes are those which are multiples of m over r. So then we measure the first register. We measure the first register. And obtain a random multiple of m over r. Obtain a random multiple of m over r. That is, we obtain k times m over r. That is, we obtain k times m over r. So k is a random number between 0 and r minus 1. Now, whenever k and m over r are relatively prime, whenever k and m over r are relatively prime, that is, whenever their GCD is equal to 1, then computing the GCD of k times m over r and m will give us m over r. Computing the GCD of k and km over r and m will give us m over r. Okay, so we know what m is from the beginning. Okay, that m is given. And we know by computing the GCD of km over r and m, now we know m over r, and we then obtain r by dividing simply m to m over r. All right, so this is just one repetition, okay, one step. But we can amplify the success probability of finding r to get close as possible to the desired value by repeating it a couple of times. So this is how Shor's algorithm works, by applying the quantum Fourier transform on the first register, and then apply the modular exponentiation function, measure the second register, and apply a partial measurement so as to eliminate the other basis states which are inconsistent with our measurements. And then after the measurement of the second register, we have a periodic superposition where the only non-zero values are multiples of r plus some offset, and then we apply another quantum Fourier transform on the first register to transform the superposition state, the period of the superposition state, to another form, so as to help us fetch the period in a better way. So let's also talk about the complexity and the running time of Shor's algorithm. Complexity of Shor's algorithm. So the best known classical algorithm for factorizing prime numbers of a given large integer is known in the literature as the field-sieve algorithm. Okay, the field-sieve algorithm, best known classical algorithm for prime number factorization. The field-sieve algorithm, and it works in exponential time. Okay, exponential time. Now, what about running time of Shor's algorithm then? So the single repetition of Shor's algorithm, most of the complexity actually comes from the modular exponentiation function. So the modular exponentiation function, UFANX, that is the modular exponentiation function. It approximately takes big O n cube time. Okay, so it's in the order of n cube. The quantum Fourier transform is in the order of, it's actually less, it's in the order of n squared, let's say. And this is a single repetition. We may repeat this algorithm to get a better approximation to R. If we repeat the algorithm log n times. So approximately the running time of the algorithm is in the order of n cube. Okay, and this is an exponential speed up over the classical algorithm, which is of exponential time, and it heavily relies on the use of the quantum Fourier transform and the power that it brings to quantum computation.